Welcome back, everyone. We're going to conclude Chapter 2 in this video. We're going to cover Section 2.3 and also Section 2.4 because it's very short. Okay, so we've got both Section 2.3 and then we'll have Section 2.4 at the end of this video. In this section for Chapter 2, we're going to be talking about other types of graphs. So if you recall from the last section, we talked about histograms, frequency polygons, and ogives. And in this section, we're going to talk about bar graphs, Pareto charts, time series graphs, pie graphs, and dot plots, which seems like it would be a lot more than what we covered in the last section. But these graphs are generally easier to construct, easier to understand, so it's actually quite a bit shorter section. And then we're also going to learn how to draw and interpret what's called a stem and leaf plot. So, first thing we're going to talk about is a bar graph. Now, when we were talking about histograms in the last sections, histograms are a type of bar graph, but they're a very specific type of bar graph. So it's kind of like when you talk about squares versus rectangles. Squares are rectangles. They're just a very specific type of rectangle where all the sides have to be the same length. Or you could even generalize it more as squares a very specific type of quadrilateral where all the angles have to be 90 and all the sides have to be equal. That's kind of like a histogram. A histogram is very specific. It's from a group frequency distribution typically. It has the classes and the frequencies, and that makes it a histogram. But it's still a type of a bar graph. Now we're going to just talk about bar graphs in general. So bar graphs represent data by using horizontal or vertical bars. That's another difference with a histogram. Histograms are only drawn vertically. They're not drawn horizontally like this first one is. Also, you'll notice there's spaces in between these bars, and with a histogram we don't leave spaces because there's no space in between the classes. And so regular bar graphs can have spaces in between the bars, or they can touch. It doesn't really matter. And then a bar graph can be used to represent qualitative data or quantitative data. These two bar graphs have qualitative data for their input: electronics, dorm, clothing, shoes, or over here, shoes, clothing, dorm decor, electronics. You'll notice the order doesn't matter. They have these in, well, kind of, it depends on if you read it from the top to the bottom or the bottom to the top, but the order doesn't really matter. In this case, they went from smallest to greatest, but you don't have to with the bar graph. And so if you were going to read this, of course, you're going to look at whatever category you're in and then go up to how high it is, and that'll tell you. So in this case, for instance, if we look at the dorm decor, it looks like the average amount spent is a little under $350, maybe about $340. Okay, so now we're going to talk about what are called compound bar graphs. And a compound bar graph, compound just means more than one. So when you compound, interest rates, it means you're like adding it on. And that's what we mean by a compound bar graph. It's just that we have more than one piece of data. So in this case, they have information for men and women listed separately. The purple bars are the men, the green bars are the women. And so for here, you could see for like the 18 to 24-year-olds, the men are at about 16 or so, and the women look like they're maybe at 18 as far as their hours. And then they have it broke up by 3 different age groups. So they have 18 to 24-year-old men and women, 25 to 54 men and women, and then 55 and over men and women. And then just as an interpretation, it says, for example, this compound bar graph shows that women watch more television than men do across several different age groups. I don't have any idea if this is real data or somebody made it up. Okay, so now we're going to talk about Pareto charts. So Pareto charts are a bar graph. You'll notice that's the first thing it says here, is a Pareto chart is a bar graph. So it's a special kind of bar graph. And the only thing different about a Pareto chart is they sort the categories from the most frequent to the least frequent. So the bars will get shorter as you go to the right. So in this case, you have the original set of data listed in this table, which is not in order. 32, 27, then back up to 44, 36, 30. These are not in order. So what they did is they arranged it with the largest category first, which is the fresh vegetables, and then smaller and smaller as you go. And then that's how they graph it on the bar graph. Again, it's still a bar graph. It's just a specific type where you go from the greatest to the least. And in this case, and often in Pareto charts, they do have the bars touch. And also with a Pareto chart, we do always make it vertical. And like I said, oftentimes they touch. Oops, that's not what I meant to do. Okay, here we go. All right, next we're going to talk about time series graph. Now, the biggest thing with a time series graph is that with a time series graph, it has to be data that occurs over a specific period of time. So in this case, you'll notice the time is months, and so the specific period of time is, it says JFMA and their months, so this is probably January, February, March, April. So for this one, it goes January to December. Now, it doesn't have to be months. It could be minutes, it could be hours, it could be days, it could be seconds. So any measurement of time can be along the bottom. But with a time series graph, one of these needs to be on the x-axis. So somehow with the data, time must be passing along the x-axis. And if that is the case, then we can call that a time series graph. Typically, they're line graphs, like this one, where we just connect the dots. And then unlike remember, frequency polygons are a type of line graph. But with time series graphs, it doesn't make sense to anchor this back, because just because we stopped here or only started here in January doesn't mean the month prior, like the prior December, was at 0. We don't know. Same thing here with December. We don't know that the next January is going to be 0. So that doesn't make sense. So we can, with the time series graphs, we can make this, it can float up above the x-axis with no anchors. So we don't need to anchor it down to the x-axis like we do with a frequency polygon. All right. And then next, similar to the compound bar graph, you can also have compound time series graphs. So in this case, remember, compound just means more than one. This one has 2. You can actually have more than 2. But in this case, we have elderly in the U.S. labor force, and they have it separated out by men and women. So in 1960, we have women at 12%, and then men at around, 33, 34%. Okay, so here's men, here's women in 1960. So we just have it separated out but graphed together. And the nice thing about that is you can compare. So in this case, it says, the percentage of elderly men in the workforce decreased from 1960 to 1990. So we're talking about, along this time period here. This went down. And then slowly increased. Okay, so then the men went back up. The percentage of elderly women decreased slightly from 1960 to 1980, and then slowly increased. And you can also talk about how far apart they are. So like in 1960, there was quite a big gap between the men and the women, but that closed up in 1990 to about the narrowest part, and then just kind of trended together after that. So from here to here is a lot less difference than there was in 1960. So it's a nice way to compare 2 pieces of data that are similar but not exactly the same. Okay, so then the next thing we're going to talk about is pie graphs. Pie graphs are a circle and that is divided into sections. Divided into sections or wedges or pieces of the pie. And with this, the biggest thing that makes, when you go to construct these, is you have to know what proportion of the data is in each piece of the pie. And it used to be, of course, if you were going to construct your own pie graph, you would have to use a protractor by hand, so something that measures angles by hand. Nowadays, you can use a Excel program or something like that to make it for you. But one of the things that I will ask on the exam, okay, I'm going to be up front. On the exam, I always try to be really upfront about what's going to be on the exam and what's not. And in this case, on the exam, I will ask you how to, or to actually compute how many degrees for one or two of the pieces of the pie. I won't ask you to do all of them because that just is too time consuming, and I can tell if you know how to do it after one or two. So I'll give you the information, and then the question will ask how many degrees, for instance, would the piece of the pie graph for popcorn be? How many degrees would it need to be? Now, it's not 3.8 million degrees. Remember, in a circle has all the way around. If you do any kind of sports where you do twists or flips or anything like that, all the way around a circle is 360 degrees. And so, sorry, my circle doesn't look very circly, but that's supposed to be a circle. And so what we do is first we find the proportion of the circle. So if we look at, for instance, the potato chips, we're going to do 11.2 million out of 30. And then once we get that, we're going to multiply it by 360 to figure out how many degrees for each slice. And then sometimes, we don't always do this, but sometimes if you want to put the percentages in the pie graph instead of the frequencies, sometimes the pie chart, sometimes the pie chart will, or the pie graph will give the actual frequencies in the pieces. Sometimes it'll give the percentage, sometimes it'll give both. So our pie graph on the next page is going to have percentages. So instead of listing the 11.2 and the 8.2, it's going to list the percentages. So let's practice this. Okay. So the potato chips, I'm going to have to get the data here. So the potato chips, we'll write these down. So the potato chips was 11.2 million. The tortilla chips was 8.2 million. The pretzels were 4.3 million. The popcorn was 3.8 million. And then the snack nuts are 2.5. Okay, so now we've got our data. And then remember, the total on this was 30 million. So all those together add up to be 30 million. So in order to get the degrees, I'm going to take 11.2 million and divide it by 30 million. And that's going to get me my percentage, or actually my decimal. Okay, so my percentage, or my proportion rather, this is approximately, put little squigglies instead of straight lines, so this means approximately equal to 0.373. But that's the decimal proportion. If we want to change that to a percentage, then we just shift the decimal over. So you'll notice here potato chips is 37.3. So that's just shifting it over 2 spots to get the percentage. But if I want to know how many degrees that is, so I'm talking about how many degrees there are here, what I want to do is I want to multiply that. So 0.373 times 360 degrees. So if I take that times 360 degrees, I find out that 37.3% of the circle of the whole 360 degrees is 134.4 degrees. Sometimes it'll ask you to round it to the nearest degree. In Alex, when you do it on the exam, I don't really care. I mean, if you show me the work, I don't care if you round it to a tenth or the whole number or whatnot, as long as you know how to calculate it. So let's continue. So this one would be 8.2 out of 30. 8.2 out of 30 is 0.27, approximately 0.2733. And if I take 0.2733, and I usually just leave on the calculator the whole thing, even though I write down a rounded version, I leave the whole thing on the calculator to be more accurate. So on my calculator, I still have the 0.2733333 with all the threes. And then I take that times 360. and that gets me 98.4 degrees. The next one, 4.3 out of 30, is approximately, I guess I could look on the pie graph because they already have it shown, so 14.3%, so 0.143. And then if I take 0.143 times 360 degrees, that gets me 51.6 degrees. And again, what we're saying is if I was measuring this with a protractor, the pretzels right here would be 51.6 degrees of the entire 360 degrees. The potato chips would be 134.4 degrees of the entire 360. Tortilla chips would be 98.4 and so on. All right, so let's continue. Popcorn out of 30, 3.8 out of 30 is approximately 0.12. It's 66666, so we're going to do about 0.127, but leave that on your calculator and then take that times 360 degrees and you get 45.6 degrees. Again, we could double check because this one actually has the something's not right on that. There's the popcorn. Pretzels, popcorn. Yes, so we can match up the popcorn here, the 0.127 with the 12.7%. Sorry, I was looking at the wrong number. So 12.7% or 0.127 is the popcorn. And then again, that would be this part in here, that's the 45.6 degrees. All right, and then last but not least, the snack nuts are 2.5 out of 30, which is approximately 0.083. You can see that on the pie chart because they already have it switched to a percentage, 8.3%. And then if we take 0.083 times 360 degrees, we get 30 degrees. So that one came out exact. So the snack nuts are exactly 30 degrees of the pie. Well, these are exact also. They just are, you have to go to the 10th for the degrees. But this one comes out to be a whole number degree 30s. Now, it says here to note that sometimes when you do this, the degrees may not add up to 360 because of rounding. So this time it does add up to 360 degrees if you add all 5 of these values. But sometimes if you've rounded these and you have to round them a little bit more than we did, sometimes they won't add up to 100%. Sometimes you'll get 99.9% or 100.1%. But again, it's because of rounding. In reality, they all add up to 100%, but the rounding makes it look like they don't. So remember, I said that I will ask you to do this on the exam. So make sure that you know how to do this process on the exam. Now, I always like to show this because some people like this process better. If you are feeling a little uncomfortable with this, there is a way to do this with cross multiplication, with setting up a proportion and doing cross multiplication. So if you like this better, you're welcome to do this. I'll show it for the potato chips. So the potato chips was 11.2 out of 30. We still start with that. But instead of dividing and then multiplying by 360, it's the same process. It's just kind of we set it up a little different. We say that equals x over 360. So we're saying 11.2 million out of 30 million is equal to how many degrees out of 360 degrees? And then for this, you're going to cross multiply. And the 11.2 times the 360 is going to give you 4,032. And then we have to divide both sides by 30. Some people don't write that intermediate step. They just multiply and then divide. But I'm going to write it down the mathematically correct way. So 4,032 divided by 30. And we get that x is 134.4. So if you like this cross multiplication method, you could do that. You start with the same thing, 11.2 out of 30, but then you set it equal to x out of 360. And then you can do a cross multiplication. Okay, so the next thing we're going to look at is a dot plot. A dot plot is very self-explanatory as far as what it is. It is plotting dots for each data value. So we take each data value and we put a dot on we plot a dot on our graph for it. So in this case, it says, so each data value is plotted as a point above the horizontal axis. So in this case, we have a random sample of 2015 model year vehicles and their miles per gallon. So one vehicle had 31 miles per gallon, the next one had 32 miles per gallon, and so on. We need to look for the smallest value that we have. So in this case, the smallest value looks like it's 23. And then we also need to look for the largest, which it looks like in this data set, the vehicle with the highest gas mileage was 36 miles per gallon. So we have to make sure we get from 23 to 36. You could go by twos, but I think it's easier to go by ones. I'm going to mark every one and then just label every other because it's a little easier. So 23, 24, 25, 26, 27, 28, 29. Here's 30, 31, 32, 33, 34, 35, and then that would be 36 and 37. We don't have one as high as 37, but I'll go ahead and mark it just to kind of finish it off. So when we go through this, we just say 31 gets a dot. 32 gets a dot. 30 gets a dot. So we've done these three. 23 gets a dot here above 23. 32 gets a dot, and since there was already a 32, we put it right above. And then 31 gets a dot. 36. We kind of try to keep these even so we can kind of compare the height of these to each other. 24, 29, 31, another 31, 30, and 31 again, and 27. So you can see from this that we have a really large grouping of data values from 29 to 32. So that's definitely the most common. Let me change colors here so I can circle that without looking weird. Okay, so, and again, we'd probably label this. We would say 2015 miles per gallon sample. Okay, and if you look, a lot of the data falls from 29 to 32. In fact, out of the 14 data values, 1, 2, 3, 4, 5 of them are right at 31. So 31 is the most common. You can see that because it's the highest. And then 30 and 32 are the next most common. And then 29 is pretty close, so I just kind of included it. But we have a lot of data. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 out of the 14 data values were from 29 to 32. Somebody said, what's the highest miles per gallon any of the vehicles in the sample had? Well, that's easy to see. It's up here at 36. Lowest is down here at 23. So you can tell a lot once you get that picture of the data rather than just in the table. All right, and now we're going to look at what are called stem and leaf plots, another real common statistical graph. The nice thing about a stem and leaf plot is that in a stem and leaf plot, like a dot plot, every data value actually gets a piece on the dot plot. It's not grouped together like it is in a histogram. So in the stem and leaf plot, this is what's known as the stem on this side of the bar, and over here is the leaf. So we look at our data values, and in this case we have everywhere from 1 is our largest, and then, or our smallest rather, and our largest is 24. And so typically we have data that's like between 0 and 100. So for the 1, for the stem, I'm going to put 0. And then I have 11, 12, 13, so I have data that's in the 10s, and then I have data that's in the 20s. If I had 30s or 40s, I'd continue. So my 1 gets plotted here at 0, 1. So the stem is typically the 10s place, and the leaf is typically the 1s place. Now you can do this with larger numbers or smaller numbers. For instance, you could have the stem be a whole number and the leaf be the tenths. But very often the stem is 10s and the leaf is 1. Okay, so we have the 1, and then the 11 would be plotted here. So 1, 1 for 11. 24 would be here, 2 for the tens place, 4 for the leaf. 17 would be here, so 1, 7. It's in the column, I'm sorry, in the row with the 1, so 1, 7. So I've done this one, this one, this one, this one. We have 12, so 1, 2. We have another 17, so another 7 in the one column, in the one row rather. 21 in the 2 row. 3 and 4 would be in the 0 row because it's 0, 3 and 0, 4. So 3 and 4. And then what we typically do is we typically will do what's called an ordered stem and leaf plot. So this is a stem and leaf plot, but most of the time what we do is we take that and then we order it. So we have 0, 1, 2, and instead of, well, 1, 3, 4 is already in order, so that one's good. 1, 7, 2, 7, let's put that as 1, 2, 7, 7 instead. For the 2, the 4 and the 1, let's put that as 1, 4. So now, what do each of these mean? If you look back at these, each piece in the leaf is a single data value. So if I said, what does this 2 right here mean? Well, that 2 was from the 12 because we've got 1, 2. If I looked at this 7, that is 17, 1, 7. And so on. Okay, so I'm going to add something to this. I've added a new data set up here because in your homework, it doesn't show it on any of our slides, but in your homework, sometimes they have you do what's called a back-to-back stem and leaf plot. So let's just kind of make up what this is. Let's say this is car dealership number 1. And this is how many cars they sold on 9 consecutive days. And let's say this new data set is dealership 2, and this is the number of cars they sold on 9 consecutive days. If we want to make what's called a back-to-back stem and leaf plot, we can compare the two. So this is dealership 1. We already did. And if we wanted to add dealership 2 on there, we could go over and put their data values on the left side. Now I'm going to kind of try to do these in order so I don't have to redo it again. So I'm going to go from the smallest. So we have a 5. And I don't see anything. Oh yes, we have a 9. Okay, so what's interesting about a back-to-back stem and leaf plot, remember we're graphing dealership 2 over here, is that a back-to-back stem and leaf plot, the data on the left side, you would never do just the left side. If you have just one set of data, you do the leaves on the right side. But if you have 2, you put one of them on the left and one of them on the right. And the values that are on the left, you read backwards. So this 5 means 0, 5. This 9 means 0, 9. And that is in order because it goes the smallest towards, the smallest number is towards the stem. So this number here, 5, 0, 5, is the smallest value. Okay, so now I'm going to go into the 20s. Or into the teens. I have a 14 and a 16. So I'm going to do the 14 closest to the stem and the 16 further away from the stem. So 14 and 16 are taken care of. And then I have 22, 24, and 25. So 22, 24, 25. So they're all in the 20 rows, and then 22, this value here, For instance, this 4 is from 24. So this would represent 24. Okay, I'm going to have to get rid of that because it's going to be in the way for my next. But that 4 that I've circled would be represent 24. All right, let me get rid of this here because it's going to be in our way. All right, now I've taken care of the 22, the 24, and the 25. I still have a 31 and a 33. Well, before I didn't have any 30s. So I'm going to extend this, and I'm still not going to put dealership 1 didn't have any in the 30, so I'm going to leave that alone, but I needed this for the 31 and the 33 from dealership 2. So now if you look at this, you can compare, and you can say, well, dealership 1 had most of its sales in the teens, or in the 10s, from 11 to 17. Dealership 2 had them more spread out and had higher values. They had some that were in the 30s. It had about a little bit over half its sales in the 20s and 30s. Whereas in this dealership, they had almost half their sales. In dealership 1 had almost half its sales in just the 10s, the 11, 12, 17, 17. So if you had to guess, you would probably say that this one has a higher average, a higher mean, because it has data values that are up in the bigger values compared to dealership 1. And so it just gives you a way to kind of compare side to side two different sets of data. On the exam, I won't do a back-to-back stem and leaf. You may have to create a single stem and leaf or interpret a stem and leaf plot that I give you, but it won't be back-to-back. But on the homework in ALEKS, there is sometimes situations where they ask you to do a back-to-back. So I want to make sure you were prepared to do that if you needed. All right, so the last thing we're going to talk about in this section are, let's see, what do we have? 1, 2, 3 different types of things that can make a graph misleading. These aren't the only things that can make a graph misleading, but sometimes when people create graphs, whether it intentionally or unintentionally, they have the graphs be somewhat misleading. So what makes this misleading? Well, this one, in these two graphs, you'll notice they have the same title. They're both vehicles on the road. They're both manufacturers, competitors, two different competitors. So competitor, I can't see what that says. What are those? What does that say? Oh, competitor 1 and competitor 2. Okay, so we have competitor 1 and we have competitor 2, and then we have the manufacturer who probably did like the study. And you'll notice the values are the same. So we have this one is a little bit above 98. This one's at about 97.5. We'll just write this down. So this is about 98. This one is about 97.5. This one looks like it's at about 96. So they're really not that much apart from each other. But this one, because they made the scale go from 0 to 100, it shows that these are pretty close to each other. So the question is, which of these graphs is misleading? The values are not very far apart from each other, but this graph shows that they're far apart from each other. It makes it look like they're far apart from each other because it starts at 95. This is the correct way to do it. The correct way to do it is to start at 0, because then you can see, oh, the manufacturer, competitor 1 and competitor 2, they really don't vary that much. You know, this one's, the competitor 2 is a little less, 2 less. This isn't a very good graph. Percent of cars on the road. Okay, so maybe like how many cars are on the road after a year or something like that. But this one says, it shows that competitor 2 is at 96% and the manufacturer is at 98. That's only a 2% difference. Whereas this, because they've chopped it off at 95, this bar right here looks like it's less than half of this bar. So it makes it look like competitor 2 has less than half the percentage of cars on the road as the manufacturer does. So the one that is misleading is the first one, because it starts at 95 on the y-axis or on the vertical scale. So the vertical scale is mislabeled, not mislabeled, but not labeled the entirely proper way. So when you start at a higher value, it makes the differences between the values seem bigger. So let's put that down. That makes the, I'm going to put it up here, makes the differences seem larger. Between the bars. Where in reality, if you start at 0, you can see they're all pretty close to 100. 98, 97.5, and 96 are all pretty close to 100. They do get a little lower, but not as dramatically lower as this first one shows. All right, so when we make a graph, if at all possible, you want that y-axis to start at 0. Okay, that's the ideal. Let me write that down too. So the ideal is start the y-axis at 0. Okay, rather than what we call this either cutting it, or another term for this is breaking the graph. Usually when we say breaking the graph, they'll do something like this. Like they'll mark the 95, and then they'll mark the 0, and then they'll put like that. So this would be your x-axis and your y-axis. So they'll put the 0, but then they'll break it and start again at 95. So either cutting the graph, breaking the graph is not ideal. We'd like to start at 0 whenever possible, like this second graph does. All right. And then the next thing we're going to look at is comparing areas. So if you look at this, these two graphs, you'll notice that in 67, it shows that we had pretty low cost for Super Bowl commercials, far less than $1 million, maybe $0.2 million or something like that. And then by 2020, that 30-second commercial was $5.5 million. So there's definitely a very large growth from 1967 to 2020. However, if you look over here, you know, you've got this little speck here for 1967 versus this giant circle for 2020. This looks like an even larger increase than this does. Well, why is that? Well, when you use 2 dimensions, so we're using a 2-dimensional shape. Instead of, I mean, a bar is a 2-dimensional shape, but we're only increasing from here to here. We're only increasing how tall it is. Okay, so we're increasing from here to here just by the height. You notice the width of this bar and the width of this bar are the same. So we truly see the magnitude of increase from the purple bar to the green bar. Whereas over here, when you use a 2-dimensional shape like a circle, this one has not only increased in the height, it is also increased in width and height. And so let's say that, let's say you had 2 bars. We'll do something real simplistic. So say you had a bar that was 1 high versus a bar that is 2 high. Okay, so from this first bar to the second bar, that's 2 times as much. But if I increase the height and the width, so I have a bar that's just 1 high, and then I put a bar next to it that is not only increased in height but also in width, then that's 4 times as big in area. So if I were to look at this bar in comparison to the first one, it looks like it's 4 times as big, even though it only increased 1 box. And so it's deceptive when you use 2-dimensional shape, because when you increase it, it not only increases the height of the green circle, but it also increases the width of the green circle. And so that's deceptive. So the second one because it increased in height and width, or it increased in two directions instead of just the height. So we only want to increase the height. So this first one only increased in the height, which is more representative of the actual data. When you do two-dimensional, it makes the increases look magnified even more. So instead of being twice as high, it's 2 times 2. If it was 5 times as high, if you use a two-dimensional shape, it would look 5 times 5 or 25 times as big. So it just is not a representative area of what actually happened. All right, and then the last one that we're going to talk about, again, there's others that you can do to be misleading, but if we look at this last slide, this is almost worse than having the broken y-axis. They don't even put a y-axis, and you'll actually see this sometimes in printed materials, but there's no y-axis on any of these. You know, so you have your cost of living, you know, north, east, south, west. You know, they don't tell us what those are, which is not helpful either. But the biggest thing is, like, how high is north? Is that at 1? Is that at 100,000? With no y-axis, these graphs really mean nothing. All we can do when we look at these, for instance, with the cost of living, is we can say north was the highest, west was the second highest, east was the third highest, south was the lowest. That's all we can say, but we can't say what any of them were. So it's when you omit the vertical scale, it makes it very difficult to understand how the categories shown compare to each other. We can't determine the actual frequencies for each class. So again, we could look at it and say, well, you know, north has the highest cost of living, and let's see, west has the highest economic growth and the highest population growth, but also the highest crime rate. East has the second lowest cost of living, the lowest economic growth, the lowest population growth, and the highest crime rate. So you can get something out of this, but it's just not going to be very detailed. So it's very misleading to not label both axes. Okay, and then our final section for chapter 2 is a section on, I have my slide here, is a section on paired data and scatter plots. Okay, so our only learning objective for this section, again, this is section 2.4, chapter 2, section 4, and our only learning objective is to draw and interpret a scatter plot for a set of paired data. So scatter plot is another type of graph. We're going to start with talking about independent and dependent variables. I'm not going to go through this pretty quickly because we've already talked about these in the last chapter. So independent and dependent variables, for instance, there's a relationship between the temperature and the chirping frequencies of snowy crickets. The snowy crickets are sometimes called thermometer crickets because as the temperature increases, so does the chirping frequency. And you can use that frequency of chirps or you can use the temperature to determine how many chirps you think that the crickets will have. So 2 measures are needed, the temperature and the chirping frequency. And then these measures are paired in such a way that the first measure, so the temperature, is the independent or explanatory variable, and that's your x value. So we talked about that in the last, I think it was the last chapter. We talked about how I cannot draw a vertical line with this application. I'm so sorry. This is horrible. All right. So you can have your x and your y. The x can either be called independent or explanatory or the input. And then the y then would be called in this case, the chirps, would be the dependent or response. So independent, y is dependent, or response, or we also can call it the output. And in this case, for this situation, this is the temperature, and this is the chirps. Now, when you're given data, you cannot switch these. However they give you the data, whatever they list as the first thing is the X. Whatever they list as the second thing is the Y. You can't say, oh, I think this might graph better if I flipped these. You can't do that. The researcher has decided what their input is and what their output is, and you have to graph that input, that explanatory variable, along the bottom. So you have to graph whatever the input is along the bottom, and you have to graph whatever the output is along the side. So whatever the first variable is has to be along the bottom. Whatever the second variable is has to be along the side when we're talking about paired data. So for a scatter plot, we're going to plot the snowy crickets. So a scatter plot is a graph of ordered pairs. I don't know why that says order pair. It should be ordered pairs. Ordered pairs of data values that are used to determine if a relationship exists. So in this case, we have a horizontal table here, but the top is the X and the bottom is the Y. If you were given it in this form, whatever's over here is the X, whatever is over here is the Y. Okay, so in this case, the snowy cricket chirps in 15 seconds, and they could do that however they wanted. They could do it in a minute, they could do it in 10 seconds, whatever, but they decided they're going to count the number of chirps in 15 seconds. And then the temperature in degrees Fahrenheit. Again, it could be degrees Celsius, degrees Kelvin, but they chose to do degrees Fahrenheit. And so we have how many chirps in 15 seconds compared to the temperature, and we're going to graph that. So you know what? I have this listed wrong on the other slide. We need to go back and fix this. I said the chirps was the output and the temperature was the input, and that is not the case. So for this table, the chirps, please go back and fix that because I don't want you to be confused when you go back and look at it. The chirps is the input, and the temperature is the output. And it's per 15 seconds. Okay, so the temperature per 15 seconds is the output and the chirps is the input. So they're saying if I know how many chirps there are, I can determine the temperature. Thus the name thermostat crickets. You can figure out what the temperature is if you can count the chirps. Okay, so let's go ahead and graph this. So we have the chirps along the bottom, and so we have 44 chirps, which would be about here, and that is when the air temperature in this case was 80.5, so just barely above 80. 46.4, just a little bit past 45, was 78. So you notice it's not perfect because in this case, more chirps was a little lower temperature. But 43.6 be a little bit past halfway between 40 and 45, and that's 78 degrees. 35 is 70.5. 32.6 would be just about half, because 32.5 would be halfway. So about halfway between 30 and 35, and that's 68 degrees. 28.9 is 66 degrees. 27.7 is 65 degrees. So we're pretty close to each other. 25.5 is 61. 20.4 is at 57. And then 12.5 chirps is our coldest. It's only 55 degrees. Okay. So that's a scatter plot. We can see that as the chirps increase, the temperature increases. And in this case, it looks like it kind of increases in a, what we would call a linear manner. It almost looks like it's kind of a line as far as the increase. Okay, so I'm going to look at their more pretty graph. So here's their pretty graph of the snowy crickets if you want to look at that. Double check that yours are in the right spots. It looks a little nicer than mine does. And then when we analyze the scatter plot, there's kind of 4 things that can happen. The first thing we want to know is the graph linear for our cases? Other times you're looking at different shapes, but in our case we're looking for, is it linear? So does it increase kind of equally, like for each certain amount of x, the y increases the same amount? That way, if you wanted to, you could write a linear equation for it. We'll do that in chapter 10, which we actually are going to do after chapter 3. So if you're in the full semester course. But we want to know, does it look like it's increasing in kind of a line? And then we also want to know, is it increasing or decreasing? So is it increasing or decreasing in kind of a line, or is it not? And then if it's not linear, is there some relationship? Okay. So if it's not a linear relationship, is there any kind of relationship? Okay. So if we look at this first graph right here, this is a positive linear relationship. And a positive linear relationship exists when the points are kind of in a line. Again, they don't have to be perfect, but if they look like they're kind of in a line, then we could say it's approximately linear. Okay, so they're kind of increasing in a line. Let me try to get this where I actually want it to be. So I'm trying to go through the middle of the points. That's a little high, but it's kind of in a line and it's going upward. So it's increasing as the x gets bigger, the y gets bigger. And so we call that a positive because it's increasing. It has an upward slope. So it has a positive slope. And so we say it's a positive and it's linear because it's kind of in a line. Same thing with this one. A negative linear relationship is going to be just the same, except it's got a negative slope. So it looks like it's kind of linear. The points are kind of trending in a downward line, but it has a negative slope. As you go from left to right, read it left to right just like you read a book, left to right, it goes downward. So we call that a negative linear relationship. As the x's get bigger, the y's get smaller. We also call that an inverse relationship. Positive linear relationship could also be called a direct linear relationship. Negative could also be an inverse linear relationship. But this book tends to use positive and negative, so we can stick with that. So a positive linear relationship, it's kind of in a line, it goes up. Negative, kind of in a line, it goes down. Now on this one, you can't say that these points don't have any relationship. You can definitely see there's something of a pattern going on here. It's just not a pattern that's a line. Maybe it's a quadratic or some other kind of polynomial shape, or maybe it's an absolute value type of thing. But there is a relationship. It's just a non-linear relationship. So they're related. They have a pattern that's going on, but they're not in a line. So it's a relationship that's not linear. And then no relationship is when it just looks like no pattern to the points. Okay, we couldn't say, oh, it looks like it's going up. You know, is it going up or is it going down? Is it staying flat? No, they're just scattered. It just looks like somebody took, a handful of pebbles and threw them at the wall, and this is the pattern that came out. There's no rhyme or reason. We can't say it has any kind of a relationship, or at least if there is any kind of relationship, it's very, very weak. So when there doesn't look to be any sort of pattern, we say there's no relationship between the input and the output. You can't use the input to predict the output. And that is it for chapter 2. So I will see everybody back for chapter 3. You should be fully ready to take on your chapter 2 homework for all the sections. And I would really recommend you give yourself more time for chapter 2 than you did for chapter 1, because it's a lot longer section than chapter 1 was. Chapter 1 was kind of like an extended section. It didn't really feel like an entire chapter. But chapter 2 has 4 distinct sections to it, and it's going to take some time to do your homework. Okay, have a good luck with your homework, and I will see you back for chapter 3.